Focus beams of electrons are used in, among other devices, electron microscopes, cathode ray tubes, and free electron lasers. For low energy applications, it might be necessary to form a 1 microamp beam of 2.5 keV electrons with a beam radius of perhaps 0.25 millimeters. Very roughly, how far might such a beam travel before its radius doubles? So the hint that we're given is that we can argue that magnetic forces are negligible and write an equation for the electron at the rim of the beam instead of, for example, a collision electron. Another hint is that we don't need to bother to solve any really big integrals except really approximately. So if we're given a natural log, then we can set it to 1 plus x or x minus 1. All right, so let's jump right into it. So given a beam, we know what the current is, we know what the kinetic energy of the beam is, and we know what the initial radius is. So let's go to the known variables, just to put a list of what we might know so we could later solve for it, and also, of course, the unknown variable. So we know what I, K, E, R, O is, but we also know what the final radius is, which is double the initial radius, and we also know what mass and charge is. The unknown variable is going to be the distance traveled, which is xf. So some possibly relevant equations that we might need to use are, of course, F equals ma, which is in the electromagnetic terms, QE plus V cross B. We need to know maybe Maxwell's equation. And it would be nice to also know the conservation of energy, or the um, kinetic energy is 1/2 mv squared, just because these are moving particles, moving electrons, and there's probably some relation between kinetic energy and velocity. So the first step we want to do is to figure out possible relations between just any of the variables we listed above and also the equations that we wrote. One nice thing that I usually like to do is to have a list of all these needed equations and variables all in front of me, so I could just always reference them and see like, oh, what am I missing, and then what can I work with on the side. So for step one, figuring out the possible relations. Okay, so we know V equals square root of 2 kinetic energy over m, so we could put that there. Originally, it was going to be the magnitude, and then there might be direction and all that. But we're assuming that since this is a beam, right, it's going in one direction only, so it's one-dimensional. You don't have to plug in any of the complicated directionality. Another thing that we can do is figure out what the electric field is. So the problem already gave a hint that this is an electron at the rim of the beam. But in general, like let's say even if the electron isn't at the rim of the beam, you'd want to probably find electric field influence on the electron to see like if it pushes the electron out, because that's probably most likely what's going to happen to cause the radius to double. So we'll solve for this using, I think it's called Gauss's equation, part of Maxwell's law. And going through this, we can integrate both sides to form the integration formula. The left side, since it is a del dot E, it's going to become the area. This is a good rule of thumb, which is that when you have when you integrate this becomes the area of E. When you integrate in general, just E in general, then it will become the volume. And when you integrate del cross E, then it'll become the length around. So it's going to become like the circle length around, circumference, let's say, around E. Why is that? It's because we're looking at the change in E. And then the change in E is going to be the derivative of E, which is going to be When integrated, it's going to be the basically the surface area of E. And then similarly, when you look at the cross of E or a cross of anything in general, you're looking at kind of the path it takes around. So integrating across that integrates the whole path, and then you'll get the the length. So knowing that, we can plug these in, and then we'll know that okay, we want to find the first of all the area of the beam. So area of the beam is what two pi RL, as you can see, because it's a circle. But then times L, which means that it turns it into a cylinder. And then finding the volume of this, I was going to write turn this into turn this into the charge, but times was it pi r squared L. Usually a lot of problems end up doing this, but in this problem, it actually might be easier to keep it as a lambda. Lambda meaning charge density per a linear charge density. So lambda is talking about the charge density, so like probably like Q, but then over the area. And then this is talking about I over V um, because if you think of it instead as I equals lambda times V, you're saying that basically current is the charge density moving. So that makes sense. And then plugging this all in, you'll get E equals I over 2 pi E epsilon over RV. So another thing we might want to solve for is the magnetic field. Um, in the solution, it already said the hint, or not the solution, the problem set, it said that the hint is that magnetic field is negligible, but we still want to show that it is actually negligible. So let's solve for B. Um, as you can see, there's a cross, so we're going to be finding the length around this circle. And then also we're going to be looking at the current and the change in electric field. This is given this equation. Oops. Okay, so given like this equation. All right. So we can assume that the change in energy or change in electric field over time is going to be zero because we're assuming a steady current. So if you have a steady current, then what happens? Then nothing. There's no mechanism to change the electric field, right? It's gonna just be basically existing. So we can remove that, and then we can make it so that okay, so the length of B around the circle is going to be mu times the current times, then you see over here J is going to be mu times current times the total current basically. And after that, you solve for this, and you get B equals mu I over 2 pi r. All right, so now that we know E, B, and V, let's simplifying assumptions because of course in physics you always assume a lot of stuff, um, and some of these may seem kind of weird, some of these may seem kind of unnecessary or maybe out of nowhere. But over here, we can show that these assumptions can be properly made and won't actually completely affect the answer to a very large degree. So the first part is saying, okay, what is it? F equals ma equals qe plus v cross b. Okay, that's a lot, especially v cross b. Cross products, especially in the solving for this part, this is going to be like a lot of solving later. So we want to say, okay, we don't want to actually solve for the v cross b part. We just want to find the qe for the f. Why can we assume that? Well, over here, as we show. So the magnetic force over the electric force, if we can show that this is very small, then we can basically say, okay, the electric force is dominant, and then you can say that it is the only quote unquote force acting on the electron. So over here, we just plug in the typical equations for the forces, and you can see that we can plug in our relations in that we got from above into these forces. And after figuring these out, you get mu e v squared. Mu e has a very famous relation, which is mu e equals 1 over c squared in a vacuum. Um, so if this were in a dielectric material or inside the inside dielectric material, this will not be the case. But we are inside a vacuum, so because it's a beam that's in air, even air counts quote unquote as a vacuum. Then you get this v squared over c squared relation, which is way less than 1, because as long as this beam is not traveling almost at the speed of light, then you'll have a beam that's non-relativistic, which is less than 1. So therefore, we can say that the force of the electric field is much greater than the force of the magnetic field. All right. Another thing we want to later ask, so over here, you'll see this probably pop up later, which is the role of collisions. So when we're talking about a beam of electrons, you're having like a million electrons or whatever, however many electrons you have inside this beam, right? And then they're going forward. So generally, if we want to solve for this, we're going to be like, oh, okay, cool. You can literally just find the time it takes to get to the end, and then multiply that by the velocity or something. Well, if you have all these like small collisions, then what's going to happen? It's going to get knocked all over the place, and then this actually might slow it down. This might make it faster. This might have unintended effects. So we want to see if these collisions actually play a role inside this calculation. All right. So do collisions play a role? We can see by using the NRL formulary. If you don't have it, I'll have it in the link below. But if you go to page 28, you'll see that the collision frequency equation is going to be this. It's this really complicated equation that was derived elsewhere. And what we'll need to know from this is probably the temperature, the ln of big lambda, and also the density of the electrons. So for the density, from before we saw that we had this linear density, which means that we could probably find the number density. The equation for linear density is going to be the charge per area, right? So we just have to multiply this by, or not charge per area, but charge times area. So you just have to divide this by the area and then also by the charge to get the number density. After plugging in all these numbers, you can try to do it yourself. It'll add up to around 5 times 10 to the negative 6 per hertz or per second of collisions. And 10 to the negative 6, that's very, very little, especially for a beam that's like traveling, it basically instantly across. So therefore, these collisions are very negligible, and we don't have to factor them in. So it's very nice because now we can assume that they're literally just particles that are moving straight across. So you can just use the very simple v equals x equals vt relation to see the distance that they travel. So yeah, this is kind of a hint as how we'll be solving for the radius or the time double, whatever, as we travel across. So first, over here, solving for the radius, we just want to find any kind of relation. So when you plug this into the what is it, F equals ma formula, you're gonna notice that okay, there's a change in radius already put into here. And all you have to do is just see, okay, what other relations can we get from this? And typically when you look at this and you integrate it, you'll be getting the time. So we'll be trying to find the time it takes for the radius to double first, and then later, if we know the time, then we can know the distance because we can find the velocity. Or we already know figured out how to find the velocity given this relation over here. So all we have to do now is find the time, and this is where a lot of the math starts coming in. So first, let's plug everything in that we know. Um, so QE equals QE is going to be or MA is going to be Q times I over 2 pi E epsilon over RV. We can simplify this by turning this into a K. So it's just simply R double dot equals K um, to times R to the negative 1, where K is going to be this. And then if you simplify this, then it'll be easier to write later. Later, we're going to try finding the integration for both of these. So R double dot and R. How do you do this? So there's usually a really well-known trick for doing this in physics. And what you do is you just multiply both sides by something in between, which is going to be R dot. So R dot is going to be directly related, is going to be just one step, one derivative of R, and then R double dot is going to be one derivative of R dot. And then you just write it in differential form. And as you can see, R dot, we'll have a R dot next to it, dr dot, and over dt, and then same with R. You can cancel out the t's on both sides, or technically you can integrate both sides by dt by moving them across and integrating. But what's going to happen is if we set t equals 0 or t0 equals 0 to t, then over here, since there's no direct relation, then you're going to get just both t's on both sides at the end, and then you can just cancel those two out. So right now we'll just cancel out the denominator t, and then we're going to be left with dr dot times r dot, and then k times r to the negative 1 dr. And you just integrate that and then get this relation. So now that we have this, okay, r dot equals this, we can try to integrate this a second time with this kind of relation again. So now that we have r dot, we just turn this into dt dr. Over here is bounded within the square root 2k and all that kind of stuff. So you just move this dt over to the other side. This is a very simple relation, simply turns into t. And then this relation over here becomes 1 over square root of something 2kln, which is going to be pretty hard to solve. Since this is pretty hard to solve, we can use the hint that was shown before, which was that we can just turn ln into the ln of whatever into that value minus 1. So let's just do that. And then now, as you can see, we can plug in the u substitution here to solve directly for the answer and get a very simple relation, which is that the time it takes for radius to double is square root of 2 over k times the original radius. And now all we have to do is multiply that by the velocity of the particle, since we know that collisions don't really matter. And after that, you multiply this, you substitute all of the values that you know, and you'll be getting this final formula. So that is going to be the answer. And if you check your work by plugging in 1 microamp, 2.5 keV, 0.255 millimeters, then you'll be getting a distance of 1.03 meters. You can check your work with that, and you can also check it with other values later on. All right. Focus beams of electrons are used in, among other devices, electron microscopes, cathode ray tubes, and free electron lasers. For low energy applications, it might be necessary to